Well, I think we can start slowly, but people start to pop up just now. Okay. Well, welcome everybody to our first seminar or webinar of the year 2015 of the Rock Glacier Inventories and Kinematic community, now officially in a standing committee of the IPA. So today it's a pleasure to me to introduce to Joe from the Chinese University in Hong Kong. Joe is a PhD student finalizing his last year of studies, and he will talk about inventorying rock glaciers for the Tibetan Plateau using deep learning. So Joe has 15 to 20 minutes for his presentation, and then the room will be open for 10 to 5 to 10 minutes of question after the presentation. So I think the floor is yours, Joe. And thank you again for willing to give a seminar.
Okay, so can you see my screen normally?
Yes.
Okay, so I will start. So thanks for the invitation for this seminar. So I'm glad to be here to share the recent publication of our work of using deep learning for mapping and inventorying rock glaciers for the Tibetan Plateau. So this paper has been recently published on Earth System Science Data to present our inventory. But in this paper, we also present a novel method of using deep learning for mapping rock glaciers. So in this presentation, I will talk about how we are going to develop this method and how to create our inventory. So first, introduction of Tibetan Plateau. So this is a vast high elevation regions in the Central Asia. So this region also has a name of the third pole because of the high elevations and the complex climate system. So this region has the largest cryosphere extent outside the polar regions, with the numerous glaciers and the vast permafrost extent. But even though for these regions, like the glaciers and the permafrost and other cryosphere components has been extensively studied, but actually there are not many studies, at least for now, about the rock glaciers for this region. Previously, by visually interpreting satellite imagery like Google Earth or InSight data, we have some studies compared the local or regional inventories for this region. But for now, a plateau-wide comprehensive and open access rock glacier inventory is still lacking. This is because mapping rock glaciers is not an easy task. For this example, maybe you can quickly identify the white glaciers and the blue lakes because of their distinct color from the surrounding environment. But rock glacier is not that easy because these debris landforms, because of the rocks on the surface of this landform, make their color very similar to the surrounding bedrock or the environment. So actually, for this region, there are many rock glaciers that just because of their similar color to the surrounding environment, it is very challenging to quickly identify these landforms and map them. So therefore, for humans, so first, we cannot use the traditional remote sensing method to map this landform, like what we do for glacier and lakes. And second, even though we ask a human by visually interpreting these landforms from the optical imagery, it's still very label intensive and time consuming. So therefore, if we want to ask a human to map rock glacier for a very extensive region like the Tibetan Plateau, it can cause very tremendous human power. So therefore, for our work, we propose to use deep learning to help us accelerate this process. A few previous studies have used deep learning to help map rock glaciers and report satisfactory results. Their studies indicate that deep learning may be a useful tool to help us map rock glaciers. But the problem is that for these previous studies, they have been limited to small regions and have not applied their model to other areas or to compile new inventory. So therefore, a systematic deep learning based and especially the transferable method for mapping rock glaciers is still absent, which forms the motivation for our work. So this is our study area, the Tibetan Plateau, which has 13 subregions of High Mountain Asia, as well as the Changtang Basin. So this is the flowchart of our method of using deep learning help map and inventory rock glaciers. For the imagery, we chose the planet-based map as the imagery for mapping rock glaciers because of its advantage. First, like it has very high spatial resolution of 5 meters, and second, it provides the quarter-based product. So for our case, we collect the third quarter in 2021. So this is the quarter is from July to September. But for this quarter product is kind of product by merging the imagery from multiple different acquisition date in order to enhance the performance of the image with the cloud mitigation and the color consistency. So these are very important, essential and important for us for mapping rock glacier over an extensive regions. And using this imagery, we extract the natural color image, the optical imagery, using the RGB band to form the optical imagery. And for the training labels, we collect the previous compiled the rock glacier inventories from 6 local inventories. But before that, we perform manual quality control. We try to manually check this compiled inventory on our own imagery and perform some quality control, like we remove some low quality samples, like the rock glaciers located in the shadow or the cloudy area. So for these samples, we remove them. And also because some previous compiled inventory, some rock glaciers that they are not really follow the latest IPA guidelines. So we try to modify the boundary of these rock glaciers according to the IPA guideline. And finally, we collect around 4,000 rock glacier boundary to form the training labels. And for them, the 70% were extracted for training, where the remaining 30% were used for validation. And for the deep learning model, we use the DeepLab version 3 plus neural network architecture. So this is a powerful semantic segmentation model. Even for now, this model is also very widely and commonly used in the remote sensing community for performing different the mapping tasks, not mapping tasks. But for now, because the deep learning, the boundaries predicted by the deep learning is still not very perfect or ready to use. So therefore, for our workflow, we still need a post-processing by manually improving the deep learning predicted rock glacier boundaries. We propose 4R operations to manually improve the deep learning predicted rock glacier boundary. Specifically, if we think that the boundary predicted by the deep learning model is very high quality, so we do not perform any operation. But if we find that the polygon predicted by the deep learning model is false positive, like what it predicts is the debris covered glacier or river or vegetation. So for this case, we will remove the polygon. But for most cases, it's the refinement. For this case, is that the deep learning model has correctly identified the rock glaciers, but the boundary is not very high quality. So for this case, we will modify the polygon boundary. And also we have a retrieve because it's possible that the deep learning model may have missed some rock glaciers. So when we manually check our each sample and perform this manual improvement during the process, and we find a missing rock glacier, so we will also add them to our inventory. So these are the accuracy metric for validating or report the performance of our deep learning model. And we also perform an independent validation of the rock glacier inventory. We randomly extract 5% of the samples, and we have two reviewers to independently validate these samples using Google Earth and assign whether this inventory rock glacier is correct or not correct based on their own experience. So for this figure, we're showing the performance of our deep learning model on the training and the validation data side. So you can say that the predicted boundaries from deep learning model actually align very closely with the training polygons. Even though for the validation polygon, we still have a good agreement, even though we may have some limitation in the routing regions. But as you can say that the boundaries predicted by deep learning model can be smoother than the human manually generated boundaries. So this can also indicate some limitations of the deep learning model to very accurately capture the local variations or local details of the rock glacier boundary. So therefore, we still need some post-processing or manual improvement. So the interception over union score for both the training and the validation data can finally achieve 0.7. So for this score, we consider it as a satisfactory result because, as I talked before, that mapping rock glaciers is a challenging task. That therefore for LU score of 0.7, it can be considered satisfactory. So after that, we applied our model to the entire study region, and the model predict around like 50,000 around candidate rock glacier polygons. After the manual checking and the improvement, we compile our plateau-wide inventory, TP-RGI version 1, which have around 45,000 rock glaciers, covering a total area of around 6,000 kilometers square. So for this slide, we can have a comparison about the deep learning mapped polygon and our manually revised polygon. So you can say, so for this example, this is a local region in Western Pamir, which our deep learning model has never seen before. However, even though for these unseen regions, the deep learning model actually perform very good because as you can see, for most of the rock glaciers, actually the deep learning model predicted boundary can have a good agreement with our manually revised boundaries, which means the prediction by the deep learning model actually perform very well. But the uncertainties still exist. Suppose like the false detection. So this can be an example. So the deep learning model predict it as a rock glacier, but when we manually check this polygon, we think it might be more like debris covered glacier rather than a rock glacier. And also there's some case about the missing identification. Suppose for this example, like for this rock glacier, maybe because they lack some distinct geomorphological characteristics. So therefore, our deep learning model may fail to capture this rock glaciers. So therefore, because of the uncertainties of this and also the inaccurate boundary. So as you can see, even though the model can map the very large area of the rock glacier, but still the boundary is not very well. So therefore, we need to also, because there's inaccurate boundary dilation, false detection, and missing identification, we still need so the deep learning model cannot directly output the very high quality or ready to use inventory. We still need the post-processing or the manual improvement to produce the real rock glacier boundary. But it can also know that the deep learning model can also help us accelerate this process. Because you think about, suppose for this region, if we ask a person to start from zero to identify and map and find these debris landforms from these valleys, it can actually cost him very long time and manpower. But if we have used deep learning to give an initial mapping and provide this candidate polygon to people and ask him only just need to perform the manual improvement, so the workload can be significantly reduced. So for this table, we show the accuracy of our deep learning model for the entire region when we use our manually revised boundary to validate the performance of our deep learning model. So over the entire study area, the F1 score is 0.6, but sub-regionally, some region can have a higher F1 score. Like for the Hongduanshan, the F1 score can be 0.7. So we consider this can be a high because considering the challenging of mapping rock glaciers. But also there are some other region like the Tibetan interior mountains, the F1 score can be lower. This is because for this region, which is the inner plateau, that the model has predicted many false positive. So this can cause a very lower precision and finally a low F1 score. And for the independent validation result, both of our two reviewers report around 87% of the inventory rock glaciers as the correct identification, and only 1% and 6% of them were signed as maybe first identification from their reviews. So this indicates that the occurrence of the misclassification of our inventory is relatively low, which is below 10%. So for this figure, I can show you some geomorphic and climatic features of our inventory rock glaciers on the Tibetan Plateau. So for most of the rock glaciers, their area is below 0.3 kilometer square. And most of the rock glaciers are in the elevation between 4,000 to 5,500 meters, and on the slope between 10 to 25 degrees. And for the aspect is predominantly face west and north. And however, for the temperature, it can have a wider temperature from -10 to 5, but most of them is between -5 to 0 for both the air temperature and ground temperature. For annual precipitation, that predominantly is below 1,000 millimeter, and the solar radiation is between 2,000 to 3,500. And the spatial analysis of the rock glacier on the Tibetan Plateau shows that the rock glaciers are widespread in the northwestern. This is a Pamir, Karakoram, and western Kunlun, and the southeastern of the plateau. So this is the Nanggun Tangula and the Hongduanshan. But however, you can see very few rock glaciers are found in the inner plateau. But for the area of the rock glacier, we find an interesting contrasting pattern that normally we find rock glacier in the northwestern plateau can have overall larger sizes. or areas than the rock glaciers in the southeastern plateau. And for the elevation, we found a gradient pattern with the higher elevations in the Ganges mountains near the Himalaya, and with a decreasing trend towards the northwestern and southeastern directions. And for the slopes, basically that in the Karakoram, Langutangula, and the eastern Hengduanshan, the rock glacier tend to situated on steeper slope. So this may be related to the local topography conditions. For this figure, which shows a pattern, the aspect pattern of the rock glacier in different subregions. So the overall trend, we can say that in the eastern plateau, the rock glaciers shows a northwestern preference, and in the central plateau, rock glacier normally facing north. But in the western plateaus, seems like rock glacier do not have a very specific preference, and seems to have aspect within every direction. So for the aspect of the rock glacier, normally it should be related to the solar radiation. But for our case, for this extensive region, seems like the aspect of rock glaciers can be more complex. So we suppose it may be also related to the complex local topographic conditions of the Tibetan Plateau. So here's the summary of our work. So for our work, we develop a deep learning based method for mapping rock glaciers, and we have demonstrated its ability for detecting and outlining rock glaciers. So this method can be readily transferred to other regions worldwide to help map and inventory to accelerate the rock glacier inventory work. And based on this method, we have developed kind of most extensive rock glacier inventory for now, TP-Rocky, which have over 40,000 rock glacier inventories and covering a very extensive region on the Tibetan Plateau. So for now, we have first extend our method from Tibetan Plateau to Hindu Kush Himalaya and the Tian Shan. So as you can see, for both the Hindu Kush Himalaya and the Tian Shan, we also find many rock glaciers that are widespread and densely distributed. And these are some examples. So you can see that for the rock glaciers with distinct geomorphological characteristics, actually the deep learning model can perform very good. Basically can outline its boundaries. Yeah, so this is all of my presentation. If you want to know more details, you can refer to this paper, and this is a paper link, and our data is freely accessible on the Zenodo. You can also scan this QR code to get our paper and data. Thank you very much for your attention, and we can discuss if you have any questions.
Thank you very much, Joe, for the presentation. You're right on time for some questions or comments from the public. I think I have two questions on the chat from Raul. If you want to read them out, please.
Let me check.
Hey, am I audible?
I say two questions. First, how the topographic characteristics are trained, like region furrow and the flow movement. How the topographic characteristics are trained, like ridges and furrow and the flow movement. I'm not very quite understand this question, but seems like the guests want to know how to make the deep learning model to learn this topographic characteristic, because it seems like we only provide the optical imagery as input, but do not provide any other topographic information like the DM or topography. Okay, so because for deep learning, what the deep learning model learn is actually is pattern. It's so it's mostly based on the I think the region of follow a very good example of the pattern. This is this is because like suppose for deep learning in deep learning community, when you look at a cat, you just say a cat suppose for a cat year. So this is a pattern, and in rock glaciers, like the region follow and also the front. So these are the pattern of the rock glacier. So for this case, because when we suppose previous studies, when people by visually interpreting the Google Earth imagery to compare the rock glacier inventory, they also just say just from the top the optical imagery, they can identify these ridges and furrows and also front. I think they do not really need the DM or slope to help them to identify the ridge and furrow. So that's exactly the same term. It's the same principle like how deep learning learn this, because they only need the optical imagery just like our human. Because I think we can identify this pattern and do not have to rely on topography data to identify this pattern. And second, how to interpret the uprooting zones of identified rock glacier, which always comes under uncertainty. Yes, I agree. Yes, very agree. So zones of identified. For rock glacier, what can be uncertain, because for rock glacier, mostly what we are more certain is about its front, maybe the region in the front. But for the routing, I agree is comes with more uncertainty. But for now, we deep learning actually deep learning cannot really help us to automatically identify this routing zone, because also because what deep learning output is actually what deep learning learn is the what kind of data we feed to it. Because in our case, I'm not sure we can. So in our case, we use the existing rock glacier inventories, even though we perform some quality control and by revising its boundaries. But I acknowledge that, because even though for this human compiled inventory, the routing zone cannot be very high with high accuracy. So even so, for our inventory, we cannot say that the routing zone of the boundary is very high accuracy. So we cannot really interpret the uprooting zone. So for our inventory, what we can for sure is first is the identification, the so-called the primary marker. But for the boundary, maybe we can for sure it's only the front and maybe natural margin. But for the routing zone, I acknowledge also for our inventory, we cannot say it can have a very accuracy for that, especially for those rock glaciers connected to the glaciers. And Nina has a question.
I can read it for you.
Oh, okay.
Or Lin, you want to say it loudly, please? Or
if transfer to other, reducing the same training data could be used, or should the training data be adjusted to each region to account for specific geomorphological difference? Have you tested or planning to do so? Again, because as you can see in our training samples, our training sample is from the local inventory from 6 different regions, also including one in the Alps, and also some other, even though for the other 5 inventory are from different regions in the Tibetan Plateau. First is that Tibetan Plateau is a very extensive regions, and I believe so. Suppose for our region, so you can say rock glaciers actually in the Pamir Karakoram and in uh, the southeast Tibet. Actually, their appearance are very different. I think maybe the rock glacier in the Pamir and the Karakoram are more like the rock glaciers in the Andes, but the rock glacier in the southeast Tibet are more like the rock glaciers in the Alps. So maybe it's because we do not just use one inventory for training, but we collect multiple different local inventory for training. So which means our inventory actually, our training data can actually learn many different patterns because the inventory is from different regions. So our model can have a large capacity to do that because actually when we use our model for predicting the rock glacier even though for this extensive Tibetan Plateau, actually it can perform very well, not just in the southeastern Eastern Tibet, but in both the northwestern Tibet and the southeastern Tibet. But I agree that whether our model is transferable to other regions we haven't confirmed that. We haven't at least to provide us some quantitative validation to confirm that. But I think the result won't be that terrible. I think I have tested it in the Austria Alps before, and I find that the result actually is, and also French Alps. Yeah, I think we have applied our model to the Austria Alps and the French Alps, and I found that the result is still is good actually. But we haven't given a very detailed look at that and provide some cognitive validation. Yeah. I'm not sure whether do you understand what I understand what yeah.
Yeah. And
Okay.
then there's another question from Raul. I can read it for you. So what are the parameters you give as a training point, sample points to the model? I intended to work on deep learning model as I'm currently doing it manually on Google Earth Pro, also identifying them through satellite imagery.
What are the training point sample point? I tend to work on deep learning as well. I am doing it manually on Google Earth Pro. Also, I think I saw satellite image. I'm not quite sure about the meaning of the training point or sample point. What that?
It's the training data, I guess, to train the model. So you explained it was like
it's parameters.
50, the parameters, yeah. I think, can you remove we see ourselves in your screen. Can you remove we don't see the presentation. Yes, please.
Okay.
Thank you.
Okay. So for this example, I'm not sure if you call the training data. So yeah, the training data is from previously already published, compiled the local inventories from different regions. So these are the training data, but I'm not sure the parameter of the training point. I'm not sure whether it's referred to the hyperparameter of the deep learning model or something about that.
Training data. So the training data comes from already published inventories.
Yeah. But if you want to know more about parameter or hyperparameter, maybe I cannot really remember some specific value. Maybe you can find this answer in our paper, I think.
Yeah. And then there's another question from Tara. I think she says, great talk. Thank you. For regions where there is not available rock glacier inventory, how does this model perform? Does it differentiate between debris covered glacier and rock glacier to a good agreement?
Can you find where there's no data performed? Does it differentiate between the rock glacier? Yeah. Well, I have an example in our yeah, for this question. Yeah, so this is example. So for this region, this is not a so this is region in Western Pamir. So for this region, there is no available rock glacier inventory before. So for this region, so it's we call it unseen region to our deep learning model. So as you can see from this slide that when when even though for this region it has no rock glacier before, and when we apply our model to this region, and you can see for most of the rock glacier, actually the result is relatively good. The boundary can align well with our manually revised rock glaciers, and it can also, for most actually are not rock glaciers, but it can say so. This blue are the glacier regions, and also include some, I think maybe include some deep recovered glacier. And also for this case, our model can differentiate between rock glacier and deep recovered glacier. But it can also happen that for this, so for example, this is a case, because there are some cases that some deep recovered glacier, it's not very typical deep recovered glacier. For this case, not our model may firstly detect it as a rock glacier. But for those very typical deep recovered glacier, I think our model can differentiate it. But yes, again, I agree that it's also a problem for mapping rock glacier to differentiate between rock glacier and the deep recovered glacier. For that, if you want the model have a really very good performance, I think one way to solve that is to improve the quality of the training data. Because for the training data, we should not first we need to feed the model with the positive rock glacier data, but also we can feed the model with the first deep recover glacier data. So this data are negative samples. So which means you told the model that this is the deep recover glacier, is not a rock glacier. So by doing this, it can enhance the model's performance to differentiate between rock glacier and the deep recover glacier. I'm not sure whether I explained it clearly. Yeah. Any further questions?
Yeah, no. Lean. Oops, a very long question.
Can you hear me?
Yes.
Yes, yeah. Sorry, I'm on my phone, so that's why I wrote. But it's not really a question, it's just a comment that I understand that not everything was possible to do till now, but I think it would be super nice to test the transferability in regions that are currently not at all included in the current training data to see if the performance is still good or decreasing. And if decreasing, it shows also the need for new training data. And if not, it shows that the current training data is basically good enough to kind of internationalize the model, basically. So that's cool.
Yeah, I'm saying what you write. Okay. There was some where deep color has time with has
but it was not really a question. It was just a comment. So I think it's a great job you have done.
Yeah, transfer. Yeah, not included in the color. Yeah. Not included in the current training data. So probably with fitting with the question. A class not listening to the first test will be trying to estimate the performance still remains good or is decreased. Oh yeah, sure. Yeah. Because for now we have more published rock glacier inventory, especially after the release of the IPA guidelines. We have just many rock glacier inventories published during the past 2 years, and also including our TP-ROGGI. So for this case, I agree that if we fed our model with more training data, the performance of our model can be further enhanced, because basically in deep learning community, people believe that with more training data, the higher performance of the deep learning model. But whether you feed the model with more training data, whether the model can become more and more powerful, which finally grew up with a model that's capable for mapping rock glacier around the world. So that is a kind of maybe ambitious, too ambitious for now, but I think that's very interesting, and yeah, maybe need more experiment, test, or validation. Yeah, I agree. The performance still remains always decreasing quite different. Yeah, and that need test, need more experiments for that. The final inventory after the model needs rigorous validation. Yeah, sure. Yeah, definitely. Because in our paper, we have different validations. The first, we validate the performance of our deep learning model, and second, we perform an independent validation of our inventory. So this is the we call this how do you say the independent validation. So for this way, you can call this is manually. This is validation is manually performed. This can be a validation of our raw glacier inventory. Yeah. So this for that way we also provide the result of the inventory the inventory. Yeah.
Okay. Thanks.
Okay,
I think we don't have any more questions. If there's a very last question or comment to Joe, please raise your hand or write it down. If there is not more questions, I would like to thank you again, Joe. There is one more from Tara. It says, can you quickly show the future work slide, please?
Feature. Oh, you want
the future, the last slide. Can you show it? Yeah. Is that what you want, Tara? Okay.
Maybe she wants to say the examples. Say what is
the example of the future work. She's writing. She's typing something.
Yeah, maybe she wants
yes, yeah. She wanted. Yes, thank you. I wanted to know the extent of the future work. Thanks. Okay.
For now, we have applied our model for mapping rock glacier to high mountain Asia. But again, because this only for now only have a deep learning mapped result. But to produce a real rock glacier boundary, there's still a manual improvement, and which is very cost the effort now. So still need some labor and time for the real rock glacier. Because finally, for this work, what we want to really produce is a rock glacier inventory for the whole high mountain Asia, or the high mountain Asia rock glacier inventory. But for now, we only have a deep learning map polygon, but we haven't done the manual improvement for now, because that, as you can see, in Hindu Kush, Himalaya, and Tianshan, there is very large quantity actually. Can also have for each region we have maybe at least 30,000. So if you want to finish performing the manual improvement for all of them, that may need very much time of manpower for doing that.
Yeah, there's a last comment from Rahul. There are always a discrepancies between a glacier as the glaciation leads to the formation of a rock glacier. How you be able to cope up with this problem, differentiating them, as there is a fine line between them?
There are always a discrepancy between glaciers.
Mm-hmm.
It's still the formation, how you can cope up with this problem of diffraction, or there is finite between the. I think this. I think this kind of to answer how to differentiate raw glacier and deep cover glacier.
Yeah, it goes
I
into
think
that question. It's not about deglaciation in this context.
It's calm, but for now, how to differentiate is only based on the geomorphological evidence, which has been listed where in the IPA guidelines. Yeah, so
For
that's
sure.
the only way we can.
Yeah,
it's the only way we can do.
Mm-hmm. Yeah, perfect. Okay, well, I think Lynn, you want to? Yes.
No, it's just that Raoul raised his hand several times. Actually, I think he wanted to comment directly.
So the model,
No, Raoul.
Raoul, yeah, he raised a hand before to see this comment, no? It's okay.
Depends on, you want to know whether the model can automatically differentiate the raw glacier and the deeper cover glacier. So again, that also depends on what kind of training data you give to the model. Because first you give the model, you tell the model that this is a raw glacier, and second, you give the model the negative samples, which is the deeper cover glacier or glacier. So you told the model that because what we feed the raw glacier is not, again, it's not point, it's polygon. So when we feed the model with the polygon of the raw glacier and the deeper cover glacier, so the model will automatically learn the boundary between them. So when they do the mapping, they were also trying to automatically identify this boundary. But again, because the uncertainty of the training data is also very high, so we cannot prove that the accuracy of the deep learning model mapped result is high. Yeah. So a quick answer is also depends on your training data.
For sure. Okay, well, thanks.
Yeah.
I think that was the last question and comment, but if you have more questions or comments, there's your contact in the presentation on the paper. So I think I want to thank you again for this presentation and being willing to answer all the questions from the community. And just to remind you, in 1 month there will be another presentation, myself this time, about insight into the geometry changes of rock glacier from high resolution 3-dimensional spatial data. So that will be the next seminar in 1 month. And from that, I don't know if there is one comment or information from the rock glacier standing committee people. Something to say? Not. With that, we conclude today, and thank you all, and see you in 1 month.